Imagine standing on the tarmac next to a Boeing 777. Looming above you is the General Electric GE90, a machine so colossal that its diameter is wider than the fuselage of a Boeing 737. It hangs there, silent, a dormant beast of titanium, nickel, and carbon fiber. It is a dead weight of nearly 18,000 pounds. In this state, it is cold. It is lifeless. It is a masterpiece of engineering potential, but right now, it is essentially a very expensive, very heavy sculpture. To wake this monster up, to take it from a cold, static lump of metal to a screaming generator of 115,000 pounds of thrust, is not a matter of turning a key. You cannot just switch it on. The physics of a jet engine creates a terrifying paradox. To run, the engine needs to compress air. To compress air, the compressor blades must be spinning at thousands of revolutions per minute. But to spin those blades, the turbine needs to extract energy from burning fuel. And here is the catch. You cannot burn the fuel until you have the compressed air to contain the explosion. It is a circular problem. You need power to get air, and you need air to get power. If you introduce fuel into a static engine and light a match, you do not get thrust. You get a bomb. The flame will not flow backward out the tailpipe, it will explode forward, melting the delicate internal structures and destroying a $30 million asset in seconds. So, how do we solve this? How do we conquer the inertia of an 18,000-pound dead weight? We have to cheat physics. We have to introduce an external force, a phantom hand that spins the heart of the engine before it ever drinks a drop of kerosene. This is the anatomy of a jet engine start sequence. It begins in silence, but deep within the aircraft's tail cone, a smaller engine is already screaming. This is the Auxiliary Power Unit, or APU. It is a small gas turbine, hidden away, spinning at nearly 40,000 revolutions per minute. Its job is not to move the plane, but to breathe life into the giants on the wings. The pilot initiates the start sequence. A signal travels at the speed of light from the cockpit overhead panel to the APU controller. A valve opens. High-pressure air, bled from the APU's compressor, surges into the aircraft's pneumatic ducts. This is not a gentle breeze. This is a violent torrent of air, pressurized to 40 or 50 pounds per square inch, hot enough to scald skin. It rushes through stainless steel pipes embedded in the wings, racing toward the massive engine pylon. It reaches the start valve. This valve is the gatekeeper. It is a butterfly valve, a metal disc sitting in the flow. When the start command is verified, an electric solenoid energizes, and the valve cycles open. The pressurized air from the tail of the plane slams into the Air Turbine Starter. The Air Turbine Starter is a mechanical marvel in its own right. It is essentially a small pneumatic motor bolted to the engine's accessory gearbox. Think of it as a high-torque windmill. The rushing air hits the turbine blades of the starter, and for the first time, movement occurs. The starter begins to spin. It screams as it accelerates, spinning up to incredibly high speeds almost instantly. But here, we face the enemy of all machinery. Static friction. Stiction. The main shaft of the jet engine, the core spool known as N2, is heavy. It carries the high-pressure compressor stages and the high-pressure turbine. It is resting on oil bearings that are currently cold and viscous. The oil has settled. The metal is clamped down by gravity. The starter motor engages a clutch, a Sprag clutch that acts like the ratchet on a bicycle. It bites into the drive shaft. The torque is transferred from the little pneumatic starter, through the accessory gearbox, and into a radial drive shaft. This shaft runs perpendicular to the engine core, diving deep into the center of the machine. At the end of that shaft is a bevel gear that meshes with the main horizontal shaft of the engine. The force is applied. The inertia fights back. But the pneumatic pressure is relentless. Slowly, majestically, the massive N2 spool begins to rotate. In the cockpit, a digital display flickers. The N2 percentage indicator lifts off 0. 0.5. 1%. 2%. Outside, the sound is eerie. It is not the roar of a jet yet. It is a low, mournful moan. This is the sound of air being sucked into the intake, the sound of the giant compressor blade slicing through the atmosphere, but moving too slow to compress it effectively. It is the sound of mechanical struggle. As the N2 shaft rotates, it forces the compressor blades to turn. This is the heart of the machine. Rows upon rows of titanium airfoils, hundreds of them, begin to sweep the air. At first, they are inefficient. They are merely paddling the air. But as the speed increases, the aerodynamics change. The blades begin to bite. They grab molecules of oxygen and nitrogen and slam them backward, squeezing them into a smaller and smaller volume. We are watching the N2 gauge. We are looking for a specific number. Usually, around 25% of the maximum rotational speed. This is the max motoring speed. Why do we wait? Why not add fuel now? Because of the airflow. If we add fuel at 10% rotation, the compressor is not pushing enough air backward. The pressure inside the combustion chamber is too low. If we ignite the fuel now, the expanding gases from the explosion will not be forced out the back of the engine by the incoming air. Instead, the fire will seek the path of least resistance. It will surge forward. It will blow back into the compressor. This is a hot start or a compressor stall. It can melt the turbine blades into an unrecognizable slag within seconds. So we wait. We let the pneumatic starter scream. We let the heavy spool build momentum. We need the airflow to be a rushing river, a unidirectional force that will carry the fire where it belongs, out the exhaust. At 25% N2, the airflow is sufficient. The pressure in the combustor is high enough to contain the reaction. Now, the pilot, or the automated FADEC computer, the full authority digital engine control, introduces the next element. The spark. Deep inside the annular combustor, buried within the dark, high-pressure heart of the engine, are the igniter plugs. These are not like the spark plugs in your car. A car spark plug fires a tiny, delicate arc. A jet engine igniter is a weapon. It receives a jolt from a high-energy exciter box, delivering 20,000 volts or more. It creates a plasma discharge, a deafening, snapping electrical arc that sounds like a gunshot. Snap. 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 You can actually hear this sound if you stand near the engine, a rhythmic, percussive clicking over the whine of the starter. We turn the ignition on before the fuel. This is a critical safety protocol. We want the spark waiting for the fuel. We never want to spray fuel into a dark chamber and then light it later. That would allow a pool of kerosene to accumulate, creating a bomb instead of a burner. The spark is snapping. The air is rushing. The N2 rotation is steady. Now, and only now, do we introduce the fuel. The fuel metering valve in the hydromechanical unit slides open. Jet A fuel, which has been waiting under pressure, rushes through the fuel manifolds. It reaches the fuel nozzles. These nozzles are masterpieces of fluid dynamics. They do not just squirt fuel. They atomize it. They force the kerosene through microscopic orifices, swirling it, shearing it, turning the liquid into a mist so fine that it behaves almost like a gas. This mist enters the combustion chamber. It hits the turbulence of the compressed air. It hits the 20,000 volt plasma arc. This is the moment of truth. Light off. In the cockpit, the pilot's eyes are glued to one gauge. EGT, exhaust gas temperature. For a heartbeat, nothing happens. Then, the numbers begin to rise. 400 degrees Celsius. 500 degrees. 600. This is the most dangerous 4 seconds in the life of the engine. The fuel is burning. The temperature is spiking. But the engine is not yet spinning fast enough to cool itself. The turbine blades, those single crystal superalloys grown in a vacuum to withstand hellish conditions, are being bathed in fire. They rely on airflow to create a boundary layer of cooling air over their surfaces. But the airflow is still building. If the EGT rises too fast, if it shoots toward the red line of 700 or 800 degrees, the pilot must abort instantly. This means the fuel-to-air ratio is wrong. There is too much fire, not enough wind. The metal will soften. It will stretch under centrifugal force. The blade tips will grind into the casing. The structural integrity of the turbine will fail. But today, the start is a good one. The EGT rises, then stabilizes. The fire is lit. The combustion is continuous. Now, the physics shifts. Until this moment, the engine was a parasite, draining energy from the pneumatic starter. But now, the fire is expanding. The burning gases are rushing rearward at supersonic speeds. They slam into the high-pressure turbine blades. This is the Brayton cycle in action. The energy of the fuel is being converted into kinetic energy. The high-pressure turbine absorbs this energy and sends it back up the shaft to the compressor. The engine begins to feed itself. The combustion creates pressure. The pressure drives the turbine. The turbine drives the compressor. The compressor packs more air. The more air, the better the burn. The better the burn, the faster the turbine. It is a runaway feedback loop of power. The N2 speed begins to accelerate rapidly. 30%. 40%. The sound changes. The low moan is replaced by a rising whine, a frequency that climbs higher and higher until it borders on ultrasonic. At around 50% N2, the engine reaches a critical threshold. Self-sustaining speed. This is the moment where the power generated by the turbine exceeds the drag of the compressor and the friction of the bearings. The engine no longer needs help. It is alive. The engine computer senses this acceleration. It sends a signal to the start valve. The valve snaps shut. The flow of air from the APU is cut off. Simultaneously, the starter motor disengages. The Sprag clutch overruns. The pawls inside the clutch, which were biting into the shaft to drive it, now lift away due to centrifugal force, hovering frictionless over the spinning race. The starter motor spins down to a halt, its job done. But the main engine is just waking up. Now we notice something else. The N1 fan, that massive, black spiral-painted fan at the very front of the engine, begins to blur. Understand the separation here. In a high-bypass turbofan engine, the big fan in the front is not mechanically connected to the compressor we just started. It is on a separate shaft, the N1 shaft, which runs through the hollow center of the N2 shaft. It is completely free-spinning relative to the core. So why does it turn? It turns because of the aerodynamic link. The exhaust gases, after passing through the high-pressure turbine, still have immense energy. They continue rearward and hit the low-pressure turbine. This second set of turbines is connected to the big fan up front. As the core screams to life, the exhaust gas wakes up the low-pressure turbine. The torque travels forward, and the giant fan blades, each one a wide-chord airfoil of carbon fiber and titanium leading edges, begin to bite into the air. This is where the thrust comes from. In a modern engine, 80 to 90% of the thrust is generated by this fan bypassing air around the core, not by the jet exhaust itself. The N1 rotation picks up. The spiral painted on the spinner cone becomes a blur, hypnotic white eye staring out from the cowling. This spiral serves a purpose. It is there to warn ground crew that the engine is running, and to scare away birds, who perceive the strobe effect as a predatory eye. The engine settles. The N2 speed stabilizes at around 60%. The N1 settles at around 20%. The EGT drops to a steady, comfortable 400 degrees. The engine is now at idle. But idle is a deceptive word. Even at idle, the internal physics are staggering. The compressor blades are spinning at thousands of revolutions per minute. The tips of the blades are experiencing centrifugal forces that make them weigh thousands of times their static weight. The tolerances between the blade tips and the engine casing are measured in thousandths of an inch. If you were to touch the casing now, the vibration would be a high-frequency hum, a testament to the precision of the balance. Inside the combustion chamber, the fire is burning continuously. It is a controlled explosion that never ends. The air entering the combustor is being decelerated to prevent it from blowing the flame out, a concept called flame holding. Imagine trying to keep a candle lit in a hurricane. That is what the fuel nozzles and combustor liner are doing every millisecond. The oil system is now fully pressurized. Scavenge pumps are sucking hot oil out of the bearing sumps, running it through heat exchangers to cool it down, and spraying it back onto the bearings. The hydraulic pumps mounted on the accessory gearbox are waking up, pressurizing the aircraft's flight controls to 3,000 pounds per square inch. The electrical generators are coming online, feeding 400 Hz of alternating current into the plane's bus bars. The beast is awake. It is hungry. It is consuming hundreds of pounds of fuel per hour just sitting there. But there is one final check. The thermal shock. The metal of the engine has gone from ambient temperature to hundreds of degrees in less than a minute. The different metals, titanium, steel, nickel, all expand at different rates. The engine is literally growing. The casing expands, the rotor expands. The engineers have calculated the thermal growth to the millimeter. If the engine is pushed to full power too soon, the rotor might expand faster than the casing, causing the blades to scrape. So the engine sits at idle. It thermally stabilizes. The heat soaks into the heavy discs of the turbine. The clearance is settled. The oil reaches operating viscosity. Only now is the engine ready for takeoff power. Only now can the pilot push the levers forward and demand the full fury of the machine. What we have just witnessed is a sequence of events that usually takes less than 60 seconds. But in those 60 seconds, we navigated a minefield of physics. We used compressed air to fight inertia. We balanced the fuel flow against the airflow to prevent a meltdown. We used a 20,000-volt arc to ignite a mist of kerosene. We managed thermal expansion, fluid dynamics, and metallurgy. Most people look at a plane and see a vehicle. But when you understand the start sequence, you see it for what it really is, a triumph of control over chaos. We are trapping the violence of a chemical explosion and forcing it to spin a fan. We are taking a dead weight and giving it a heartbeat of fire. It seems simple. You turn a switch. The engine starts. But behind that switch lies a century of thermodynamics, tragedy, and engineering brilliance. Every successful start is a victory against the laws of nature that would prefer the metal to melt and the fire to explode. To keep deconstructing the world's most complex systems, stay connected to Gridonix.